Hello everyone, I am Devan Mukherjee and my topic of presentation is learning to match schemas using knowledge graph. The schema matching problem has been a crucial task across industries which finds out a field level one-to-one mapping between two relational schemas named target and the source schema. This is the first and one of the most important problem for data migration. Typically, in this problem, a single internal target schema is maintained which is matched with different source schemas over time, and thus the problem is referred as target-driven schema matching problem. In the schema matching task, though the target and the source schema belong to the same domain, they are very different in their surface form. Same semantic concepts appear differently across field names. For example, start date and effective date both represents the same meaningful item. The automation of this problem produces a schema matching recommendation by creating a ranked list of source field for each target field. To solve this problem, apart from two schemas, domain knowledge information is necessary, which captures the relationship between concepts. The domain information is represented using knowledge graph or KG, which represents concept as vertices and relationships as edges. For example, both start date and effective date are concepts having a synonym edge between them and so on. Among two different state-of-the-art approaches, the first type applies KG to solve the problem. The solution named Cupid extracts token from column names and applies token relations between field names using handcrafted domain knowledge. And here lies the shortcoming of this problem, that the handcrafted domain knowledge used is not scalable and existing domain information is not sufficient. Apart from schemas and KG, there can also be some historical matching data containing matching between single target schema and many other historically matched source schema is typically available as evidence for matching. All those evidences can be reused for matching a new source schema called the test source schema. Now, the second state-of-the-art approach named LSD is learning-based, which is capable to learn from historical matches, but it models the problem as a classification task, for which each target field becomes a class label where the source field is treated as data points. Clearly, it won't work well as typically and there lies thousands of fields under the target schema and historically matched source schemas are in tens. Uh, which depicts that thousands of class labels are there where on an average smaller than one label training data are there for each class. So in practice, so many crucial evidences of matching gets missing in industrial dataset. Uh, all those things include unaccessible uh, data under the fields for some legal issues, structure of the schema beyond tables and columns such as primary and foreign key information, etc. Also, field names under a database are often cryptic, containing abbreviations and acronyms. Thus, the problem is solved manually by domain experts till now, which requires extensive human involvement with enriched domain expertise, taking almost 6 months or even more to match one source schema with the internal target schema. So, considering all the shortcomings of the state of the art approaches and the constraint over the real dataset, we propose a solution which mimics the approaches taken by domain experts. It learns at the level of concepts and relationship between concepts rather than fields. It also learns probabilities of concepts and relationships being used in matching and finds out new concepts and relationships from historical matching information. So technically, at a high level, our approach infer matching between a pair of fields by finding out concept decomposition for each field name and aligning concepts of a field pair based on their relationships. The problem is equivalent to identifying the bipartite graph with the best matching as a subgraph of a very large graph. In the learning task, the probabilities of the concepts and relationships are acquired from the concept decomposition and alignment among historically matched field pairs. As all the concept decomposition and alignments in the historical matchings are unobserved, inferring all these things are required. As a solution to our technical problem, Monte Carlo approximation using sampling is used for inference and stochastic expectation maximization is used for learning. Now let us understand with an example of how two field fx from target schema and fy from the source schema are matched. For each field, a name is associated with it, which is represented by a sequence of tokens named lx and ly respectively for target and the source schema. The name of the field is directly observed from the schema. On the other hand, a concept sequence C is also gets associated with each field representing the semantic interpretation of a field which is unobserved. For example, the concept sequence Cx represents the field is about expiry date of benefit of contributor in the context of escalation of benefits. Finally, concepts from two different fields are aligned and thus the unobserved alignment variable A gets associated with a pair of fields. We call Cx and Cy as schema latent variables as they are related to the standalone schema element or field, where A is called matching latent variable as they appear while matching. Now, we have introduced the KG as a combination of three elements C, R, and W, where C is the set of vertices representing concepts, R is the set of edges representing the relationship between concepts, and weights W associated to both vertices and edges of this graph. Now, weight WC associated with concept vertices represents the probability of a concept to appear under concept decomposition of any field name. On the other hand, weights WCC prime associated with edges represents the probability of a concept pair to appear under the alignment uh, between a pair of fields. Now first we define the joint distribution over the pair of matched field names and latent variables in terms of kg weights. From the joint distribution, we can construct the posterior over the latent variables to address the inference problem. Now, finally, the inference task is to find out the most likely assignment to the latent concept decomposition and alignment variable given the observed field names. It is obtained by getting single sample from the posterior distribution over the hidden variables. Now, the search space to find out all possible concept decomposition and alignment between two field names and get the optimal one is combinatorially explosive. And thus, we introduce Monte Carlo approximation that samples one aligned concept pair at a time. And successive sampling of the aligned concept pairs form a complete alignment. For that, we have constructed conditional distribution of nth aligned concept pair given the selection of the first n minus 1 aligned concept pair on top of the sample space of possible alignment edges or aligned concept pairs. So here we explain it in details. Now to solve the inference problem, first the set of all possible concepts from both Lx and Ly named C of Lx and C of Ly is constructed. As an example, concept from Lx can be benefit, benefit escalation, contributor, escalation, contributor, and so on. Afterwards, we construct the search space of all aligned concept pairs by taking Cartesian product between C of Lx and C of Ly, and we create distribution on top of it considering the kg weights. From this distribution, we iteratively sample aligned concept pairs and remove all other concept pairs from the distribution having the overlapping concept with the sampled one. This is how we construct the conditional distribution of the nth alignment edge given the first n minus 1 alignment edges. And finally, we construct the complete alignment between the field pairs by successive sampling from the conditional distribution until all the concepts from both the fields are sampled. Now, on the other task, in the learning task, given historical matching information image, our goal is to find the optimal kg parameters which maximizes likelihood of the matching for the historical data. We formalize the task as a maximum likelihood estimation problem involving hidden variables with respect to the kg. Here hk depicts the hidden variables for the kth field pair. In other words, the task is to find the concept relationships and associated weights that maximizes the alignment between the training set of matched field pairs. We use an iterative learning algorithm based on the stochastic expectation maximization framework, applying the intuition that existing kg probabilities can be used to infer latent variables, and in turn, all these inferred latent variables can be used to update the probabilities in the kg. So, as a solution, we have proposed a stochastic EM or stochastic expectation maximization framework where in each step the latent variables are inferred for each of the historically matched field pairs, and in M step the kg parameters are updated based on the number of occurrences of the concepts and concept pairs along appearing under the latent variables altogether. And now we introduce source specific learning where we consider a small subset of the output matching is initially available as input. Due to the evidence that some concept relations, the same concept relations appear in many field matches for the same source, learning concepts and relationship from the source specific input impacts the performance significantly. The baseline LSD cannot apply it because LSD learns at the field level of field instead of the level of concepts. Now, one another subproblem for the schema matching has been addressed in our solution. Industrial data often contains cryptic physical name, including abbreviations and an acronym inside it. Like field name, policy coverage termination date appears as Polkov term DT under the schema. Thus, expansion of these names are required to get the proper field name. This problem is equivalent to finding optimal state sequence in HMM, where cryptic physical token sequence is observed and expanded token sequence is latent. Due to the large subspace over all possible expansion for each cryptic physical token, we approximated the solution using lazy-Viterbi algorithm. Now getting to the experiment, first we show the data statistics for both the benchmark purchase order dataset and the industrial insurance dataset. So first, pure is a XML uh, uh, dataset which contains 5 schemas, and matching for each of the 20 pairs among them are also there in the pure dataset. As we have proposed our solution on top of the relational database, we concatenated names from root node to the leaf node in the XML schema along one path to get the field name corresponding to a relational schema. We experimented with each of the 20 pair of schemas as target and the test source, where for each pair, the remaining 3 schemas are treated as training sources. Now getting into the stats, average number of fields along with the number of gold standard matching pairs are a lot more in insurance dataset compared to the pure dataset. On the other hand, for learning, the ratio of historical matching size and the number of target fields is significantly higher for the PO compared to the insurance, which implies that insurance has a very little historical data for field level learning, unlike PO. Also, in insurance, all the sources aside from S4 contained only physical names for fields and not the expanded field names. All the experiment conducted by us has been evaluated with the metric MRR or mean reciprocal rank. The MRR has been calculated over the rank of the gold standard field appearing under the ranked list of the source field for each of the target fields. Now from this table we see out of 20 experiment, 13 out of 20 won by magical, 5 out of the 20 is won by LSD, and 2 out of 20 are tied between LSD and our solution magical. Cupid has no win over here as no domain information was provided in this case. Now, analyzing wins of LSD, it was found out that LSD learns at the level of individual fields, and when a source field name appearing in training repeats in the test, LSD can effectively remember and reproduce the field level matches. On the other hand, our solution learns at the level of concepts and is able to find out and use the meaningful concept pairs for matching even from the small number of historical matches in PO. In addition, our solution is able to learn from feedback matches for the test source, unlike LSD, causing a significant performance boost. Now we show the outcome over the insurance dataset where our solution outperforms baseline significantly because of the concept level learning instead of the field level learning. We have also shown how the result gradually improves by introducing domain knowledge and learning for both the baselines and our solution magical. It has been reported here as plus K and plus L respectively. We also show the advancement of the outcome by introducing source specific learning for 4 source schemas. Now we have shown how the domain knowledge in historical matching data and source specific learning improves the performance individually. So our performance can get even better by acquiring more and more such information from domain experts. So the overall summary of this paper is introduction of a probabilistic framework for schema matching, including a KG of concepts and relationship. Based on stochastic EM framework, KG elements are learned from historical matching data. We have also shown performance of our solution in contrast to the 2 state-of-the-art baselines. And finally, our proposed work is the first significant step towards automating the data migration via learning. Thank you.